are meeting again to continue our discussion on the electrochemical technology. I have been trying to introduce you to solution chemistry as part of the course, and we had discussed about activity and activity coefficient in the last class. You can look at the slide now. Here I have written an equation that is A plus B going to AB. The concentrations are here, but instead of concentrations, thermodynamically, to be very correct, we should write A plus and A into B AB plus divided by AAB. Here A represents small a represents the activity of A, and A B plus represents activity of B, and AAB represents the activity of AB product. So, activity is defined as the concentration into activity coefficient. We had also discussed about a little bit about the ionic strength, that is the activity is nothing but activity coefficient into concentration. So, we have defined ionic strength as the total number of ions present along and their product of ionic concentration and valency, sum of that, and approximately 50% as the ionic strength. So, then we discussed about the acid base equilibrium reaction. We have written acetic acid plus H2O going to H3O plus and CH3COO minus. We write an equilibrium reaction constant K is equal to CH3COO minus and H plus into CH3COO minus CH3COOH, and if 1 gram equivalent is there and a small portion, that is alpha, dissociates into the products, I can write undissociated product would be 1 minus alpha. So, I can write instead of H3O plus and CH3COO minus, I can write alpha alpha. So, alpha square divided by 1 minus alpha into V, that is alpha square C divided by 1 minus alpha. So, this is the dissociation constant, and the values of alpha can be determined experimentally by determining the equivalent conductance, because those things, these H3O plus and CH3CO minus contribute to the conductance, this will not contribute. So, I can determine the conductance and take 50% as H3O plus and 50% as CH3COO minus of the total conductivity. Okay. So, that is lambda C of the analytical solutions, and we assume that it is the conductance at infinite dilution. So, the dissociation constants of weak acids are available in the literature, and now up to this we had done earlier. Now, we are going to discuss about the weak bases, that is dissociation of weak bases. Just like acids, we also have bases. Bases can be strong bases and weak bases. Sodium hydroxide, potassium hydroxide, they are all strong bases. Ammonia is a weak base. So, you can smell ammonia very easily, no, because it is a weak base. So, ammonia will react with water to give you ammonium hydroxide. The reaction is represented like this: NH3 plus H2O going to NH4 plus and OH minus. Okay. There is another equilibrium that is present in aqueous solutions, that is water itself can dissociate as H plus and OH minus going to H2O. So, I can write Kb is nothing but NH4 plus into OH minus and divided by NH3, that is the product. We do not write the concentration of water because it is very large compared to NH3. So, it is we assume that it is 1, all others are very small. So, we have Kb, the dissociation constant of ammonia is nothing but NH4 plus into OH minus divided by NH3 plus, and I can write an equilibrium constant there is, because this is equally available. simultaneously going on, I can write Kb is equal to Kw by Ka. This is the equivalent concentrations of water is written as Kw. I can write here similar equation H plus into OH minus divided by H2O, that is Kw. Okay. So, since values of Kb and Ka vary over several powers of 10, that is you remember what is the value of Ka, that is for acetic acid, it is 1.85 into 10 raised to minus 5. Who will remember so much, 10 raised to minus 5, 10 raised to minus 6. For day to day life, it does not make much sense to remember all this. So, what we do is we write use a value that is logarithms. So, 10 raised to minus 5 is 5 minus 5, the log of 10 raised to minus 5. So, we use pk as we define pk as negative log of k to the power of 10 to the base of 10. So, here if I write 10 raised to minus 5, it will be larger, it will be 5 point something, 4.87 into 10 raised to minus 5, that is what it means pk. So, larger the pk, weaker is the acid and stronger is the base. This is the ultimate conclusion of the pk value. So, if you see the value of pk in it means you are seeing the value of negative log of 10 k. So, if pk is larger, the acid is weak and base is strong. So, larger pkb, weaker is the base and stronger is the acid, very simple to understand. And this is about the dissociation constant. Now, I will discuss about the common ion effect, that is concentration of a particular ion in a solution can be increased by the addition of another compound which produces the same cation or anion. I want you to imagine that we are having a particular solution of acetic acid. Okay. Now, acetic acid will dissolve into acetate ion and H plus ion. We have written the equation earlier, you can see the previous slides. So, what we have written, CH3COOH going to CH3COO minus and H plus. Okay. Now, to this solution containing CH3COO minus and H plus and CH3COH, undissociated acetic acid, to this if we add, I want to add sodium acetate additionally from my shelf, then what happens, we have another equilibrium in the system, isn't it? So, look at the slide now, that is what I am going to explain to you. Here I am writing CH3COOH going to CH3COO minus and H plus. To this solution we are going to add sodium acetate and we have another equilibrium for sodium acetate separately. What is that equilibrium? Sodium acetate will decompose into CH3COO minus and Na plus. Okay. So, if I add this, there will be two equilibriums in the same solution. One is acetic acid, another is sodium acetate, but look at this. This CH3COO minus is common here in this equation, okay, and CH3COO Na is also going to produce CH3COO minus and Na plus. Okay. In general, you have to understand that 99% of the salts are ionized, sodium salts are ionized 100%. All sodium salts and potassium salts. 99% of them are totally ionized, 100% ionized in solution. So, if I add sodium acetate to acetic acid, what I am going to add? 100% ionization. So, I am going to add CH3COO minus ions to the same solution and a little bit 100% of sodium ions plus whatever that can come from acetic acid in this case. So, in the solution we have CH3COO minus coming from this reaction and another CH3COO minus coming from this reaction and Na plus and H plus. So, this is common. So, this is what we are discussing. This is what effect this addition of CH3COO will have on the dissociation constant of CH3COOH. So, unlike acetic acid, sodium acetate is 100% ionized. Therefore, the concentration of CH3COO minus will be much more than what is produced by the dissociation of acetic acid. So, this induces the backward reaction of the acetic acid with the result that the acetate, more acetate ions will be converted into acetic acid. Go back now. Here consider this. Now, I have more of this and less of this, more of this. So, remember Le-Chatelier's principle. If I add additional CH3COO minus into this system, the system should try to remove the addition. So, how will it remove the addition of CH3COO minus? It will combine more with H plus and go back to CH3COOH. That means, the dissociation of acetic acid will become less to the extent of the effect of CH3COO minus coming from sodium acetate. So, this effect is known as Coben ion effect. So, Le-Chatelier's principle is at work here and it will induce more of the acetate ions to get converted into acetic acid. Okay. So, this is the principle of common ion effect. So, now we are going to talk about the solubility product. So far I have been trying to introduce you to different concepts of the aqueous chemistry. Okay. So, now we have discussed about activity, concentration, dissociation and then common ion effect and all those things. Now, I am going to introduce to you one more property of the aqueous solutions. That means, they contain solutes dissolved in the solvents. So, earlier we have talked about solubility. Now, I am going to talk about the solubility product. Okay. Now, look at the slide now. I have a product salt AB. Okay. It is S I have written here. It represents sparingly soluble salt. Okay. S means salt. Okay. Solid. It can also represent solid. So, for sparingly soluble salts, what does sparingly soluble salt mean? It means it is very soluble, very less extent. That means, even if you take the solid, put it in water, it will remain as such, but water will be saturated with the ions of the salt. So, but very little salt will be dissolved in water. Such a thing is known as sparingly soluble salt. For example, I can choose silver chloride. Okay, all students of chemistry or high school students, PUC students, college students use it as a chemical test for the chloride. That is, if you add silver nitrate solution to a silver nitrate solution to a solution containing chloride, silver chloride will precipitate. So, why silver chloride will precipitate? Because the solubility of silver chloride is very less in water. Such a substance, whenever there is a precipitation reaction happening, it means the solubility is very less. Such product like silver chloride is known as sparingly soluble salt. It may be of the order of few milligrams per liter, okay, few milligrams per liter, or it may be few grams per liter, but definitely not more than that. Okay. It may be a few micrograms per liter. Okay. So, we are going to talk about such salts which are very sparingly soluble in water. So, for earlier you also remember that I have talked to you about the dissociation. All salts, dissolved salts in water, they dissociate into their corresponding anion and cations, positively charged cations and negatively charged anions. Sodium chloride will give you positively charged sodium, negatively charged chloride ion. So, I am going to write an equation for the equilibrium between undissociated salt and dissociated salt in water in aqueous solution. So, I write here AgCl, this is a specific example. AgCl solid is in equilibrium with Ag plus and Cl minus ions in water. This is the actual example, this is the general example. AB solid is going to A plus B minus. So, we can write an equilibrium constant for this reaction, okay, involving both forward and reverse reactions, just like a dissociation constant. So, I write SAgCl, that is at the bottom I should write Ag plus into Cl minus divided by AgCl. Now, I can write an equilibrium constant K is equal to Ag plus into Cl minus divided by AgCl. This is also concentration. Now, you should remember that AgCl is a solid, okay, because it is very sparingly soluble. The product AgCl at the bottom is a solid. So, concentration of solid is always 1, remember that. You must always remember that the concentrations of solids in their solid form is 1. So, I do not write, I can simply write K is equal to Ag plus, if the denominator is 1, I can write Ag plus into Cl minus is equal to K, because of AgCl is 1. So, here I am writing AgCl is equal to Ag plus into Cl minus forward reaction. For the reverse reaction, I should write AgCl divided by Ag plus and Cl minus. This is for the forward reaction. And K2 I can write, this I can write it as K1, K2 would be AgCl divided by Ag plus into Cl minus. Okay. So, This is the ratio K1 by K2. Here also it should be K1 only. No. So, K1. So, K1 by K2 is nothing but the product of Ag plus and Cl minus. Here it should be Ag. There is an error, typographical error, G plus is there. So, here it should be Ag plus into Cl minus, because AgCl is 1. So, a large database exists again for the solubilities of sparingly soluble salts in water and several other solvents. Okay. So, I will not discuss more about sparingly soluble salts, but you are introduced to the concept now, is not it? Now, I want to introduce you to another property of the solutions, that is ionic product of water. What can happen water do? One molecule of water may react with one more molecule of water to give you H3O plus and OH minus. Here it should be H3O plus. A positive charge, it is a cation. Okay. So, H3O plus into OH minus ion. So, we can apply the same law of mass action or equilibrium constant to this reaction, and I can write AH plus activity of the hydrogen ion into activity of OH minus ion divided by activity of H2O water molecules, and I can convert it into concentration because it is only pure water. So, the reaction can be written in terms of concentrations and activity products, and activity products are 1 almost in all water solutions. So, I can write this is 1 H2O, the value of H2O would be 1, and these are all 1 into 1 divided by 1. So, I can write the product of H plus and OH minus ion is equal to a constant, that is known as Kw. Very popularly known, people write this Kw. Every time you write dissociation of water, you simply write Kw. So, this value you should always remember that it is 1 into 10 raised to minus 14, sorry, 10 raised to minus 14. So, what would be the value of H plus? H plus would be 10 raised to minus 7, and OH minus also should be equal to 10 raised to minus 7. Then only Kw would be 1 into 10 raised to minus 14. So, this Kw is known as ionic product of water because it is the product. Two values are there, which is 10 raised to minus 7 and 10 raised to minus 7. So, H plus is equal to 10 raised to minus 7, OH minus ion concentration is equal to 10 raised to minus 7. So, it is called as neutral solution. So, H plus is greater than 10 raised to minus 7, we call it as acidic, and if H plus Kw H plus is less than 10 raised to minus 7, then it is called as basic solution, base solution. Okay. So, this concept of ionic product of water is a very important concept. So, that brings us to the discussion of what is a pH. So, you should remember that we are writing almost all things in the negative log domain. So, to express the hydrogen ion concentration again, In pure water it is H plus is 10 raised to minus 7, and then in acidic solutions it may be 10 raised to minus 2, 10 raised to minus 5, it may be 10 raised to minus 1, it can be anything. So, again these 10 raised to minus 7 exponential terms are difficult to handle, difficult to remember. So, the concept of log value has been introduced, and even to write the H plus concentration, we this gentleman, he is a great scientist actually, SPL Sorensen, proposed that instead of writing 10 raised to minus so much, so much, so much, etc., you simply write it as negative log of concentration. That will be very simple number. So, he suggested that use logarithm to the base of 10. So, this is very widely accepted all over the world. So, pH it is called as pH is negative log of H plus ion, that is log of 1 plus 1 divided by H plus. This is nothing, this expression can also be written like this, or 10 raised to minus pH or 10 raised to minus pOH. So, if H plus is 10 raised to minus 7, OH is 10 raised to minus 7, Kw is 10 raised to minus 14, pKw is 14. It becomes 10, instead of 10 raised to minus 14, it becomes 10 raised to 14. This becomes 10 raised to minus 7, but in pH scale it becomes 7. This is concentration is 7, and if there is no H plus, it becomes 10 raised to minus 7. Okay. So, Kw is 10 raised to minus 7. So, there are 7 regions of OH minus, 7 numbers up to 7, and 7 numbers for hydrogen. So, we say pH 7, we divide pKw 14 exactly. So, half of this is 7. So, pH 7 is a neutral solution. Anything above that 8, 9, 10, 11, etc., it is a basic solution, and if it is less than that, it is acidic solutions. So, we have this expression. The next thing we want to discuss is about the hydrolysis of the salts. So, how many salts are there? There are n number of salts, thousands of salts, but many of the salts dissolve in water, and that process is known as hydrolysis. Okay. So, I can have, there are 4 kinds of salts, okay. Salts of strong acid, hydrochloric acid you all know. So, a salt of strong acid like sodium chloride, potassium nitrate, etc. And that is sodium chloride, they are all salts of strong acid and strong bases. Okay. And then salts of strong acids and weak bases are there. Ammonium chloride. Ammonia is a weak base, chloride is a salt of strong base. So, I have here salt of strong acid and weak base. Okay. Ammonia is a weak base. So, sodium chloride, weak base and strong acid, strong base. Sodium hydroxide is a strong base, hydrochloric acid is a strong base. So, NaCl is a strong base, salt of strong acid and strong base. So, KCl also ditto. KNO3, it is salt of nitric acid. Here I have salt of strong acid and weak base, you remember, like this. and then salt, I can have salt of weak acid and strong base CH3COONA. This is a strong base. If I make a base out of this, add a OH, it becomes a very strong base, but CH3COO minus is a weak base, weak acid. Then I can have salts of weak acid and strong base, weak acid and weak base. Ammonium acetate, CH3COO NH4, or CH3COO thrice, aluminum acetate. These are all aluminum is also a very weak base, acetic acid is also a weak acid. So, I have salt of weak acid and weak base. So, interaction with water of all such salts, of all these salts, may change it to neutral or acidic or alkaline, any of these things, is not it? Because they are all going to dissociate in water. So, I have a case 1 here, strong acid and strong base, that is H plus and OH minus ion equilibrium is not disturbed and the solution remains neutral. If I take a strong acid and strong base, salt of a strong acid and strong base, I have only H plus and OH minus ions are not disturbed. So, NaCl, where is H plus and where is OH minus? In NaCl, nothing. So, Na plus and Cl minus will be there. So, the pH will remain constant, it will not change if I put it in water. So, but if I take weak acid and strong base salt, then what happens? pH would be the half of this pKw, that is the dissociation constant of the water and dissociation constant of the acid plus 1/2 log of concentration of the salt. So, there is a certain amount of derivation of this equation in the book by Vogel, 3rd edition, Quantitative Inorganic Chemistry, and this expression is usually used to determine the pH of a solution containing a salt of a weak acid and strong base. Here if I know the concentration of the salt, I can this data pKw and pKa are available from database. pKw is always 14 now. So, half of pKw is 7. So, I can always calculate what is the pH. pH measurement is a day to day affair in all chemistry labs and pollution control labs. So, it is in whatever you do, whatever salts you have, the one of the activity is to find out the pH of the solutions. So, if I have a salt of strong acid and weak base, I can write an expression like this: 1/2 pKw minus 1/2 pKb minus 1/2 log C. That will give me the pH. That is, if I know the concentration of the salt, I can simply calculate the pH and check whether it is correct or wrong. So, I do not have to go to a laboratory to check the pH. If you tell me that you have dissolved so much salt, a salt of a strong acid and weak base. Okay. So, it is another way of putting it. Now, then I have case 3, that is weak acid and weak base. Here also I can write pH is nothing but pKa logarithm of the ratio of salt to acid, weak acid weak base now, or salt to acid, that will give me POH. That is, just like pH we can write POH, and pKb if I know, I can write PO, find out what is POH, whether it is 9 or 8 or something like that. So, we are going to discuss about hydrolysis. What is hydrolysis? I am writing H2O plus as H plus and OH minus, and I can write a salt Ma as M plus and A minus. M represents metal. it may be sodium, potassium or anything, A may be acetic acid or any other salt. So, the A minus ions will react with H plus to give me HA. Since part of H plus ions are consumed, H plus ion concentration will decrease. Part of H plus is consumed, so HA is formed, this is undissociated. So, the pH should decrease. So, disrupting the equilibrium in equation 1. So, to compensate for this decrease, more water will dissociate producing H plus and OH minus ions. Since that is Le Chatelier's principle again. Since OH minus ions decrease the solution, increase the solution becomes more alkaline. Hence, we can write A minus plus H2O going to OH minus plus HI. The reverse reaction in this case is more predominant. That is what I am trying to drive. So, the interaction between the ions of the salt and ions of water is known as hydrolysis. So, the hydrolysis of weak acid and strong base produces a weak acid and or a weak base, and or both a weak acid and weak base. We can write AOH into AHA divided by AA minus, that is in concentration term. This is FOH into FHA, that is the activity coefficient. All these we have discussed earlier. So, the degree of hydrolysis is the fraction of each gram molecule hydrolyzed at equilibrium. This is the definition. The degree of hydrolysis is the fraction of each gram molecule hydrolyzed at equilibrium. Mathematically, I can write a similar expression like a dissociation constant, that is x square divided by 1 minus x r into V, that is the degree of hydrolysis, that is symbol is Kh. So, degree of hydrolysis leads us to the situation of buffer solutions. So, what is a buffer solution? We consider a mixture of weak acid or a weak base, dissociation constant pH is equal to pKa plus log of salt or acid into Kb. So, salt and acids are equal, strong pH is equal to pK. So, if we add a small quantity of 0.1 normal acetic acid, then Ka plus CH3COO minus will become CH3COOH. Here it should be H plus. Okay. Please correct this. Here it should be H plus. So, it will combine with acetate ions from undissolved acetic acid. Similarly, if I add a small concentration of OH minus ions, it will combine with H plus to form undissolved water. So, in effect the pH remains unaffected. So, in either case the pH of the solution will not change appreciably, since the concentration of the acid will remain unchanged. Such solutions are called buffer solutions. So, buffer capacity is maximum when acid to salt is 1:1 ratio. For acid to salt 1:3, pH is given by this expression pKa log of minus log of 1/3. For acids it is pKa plus 0.48, and the appropriate approximate pH range for buffer capacity is, if you add 10 times acid or salt, buffer solutions find the pH will not change appreciably. The buffer solutions find many applications in chemical preparations, quantitative analysis, precipitations, electrodepositions, etc. So, here we come to the end of our general chemistry introduction to electrochemical techniques, and from the next class we will start looking at the electrochemical techniques in particular. So, thank you very much. We will continue our discussion in the next class.